In the first rational function video, we talked about how to find x-intercepts, y-intercepts, vertical asymptotes, and determine the domain of a rational function. Remember, a rational function is a function that is made up of a fraction where the numerator and denominator are both polynomials. Today, we're going to focus on how to determine where horizontal and slant asymptotes are located, and how to sketch a rational function without a calculator. Make sure you've got your paper set up in Cornell Note format, and the essential question and the title need to be at the top of the page. Okay. So a rational function can have three different types of asymptotes. We've already talked about vertical asymptotes, which we found by setting the denominator of the function equal to 0 and solving. Okay, the other two types are horizontal and slant. A horizontal asymptote is also known as an end behavior asymptote because it tells you what the graph is doing on the very far away from 0 as x is approaching positive or negative infinity. So as my x values get larger and larger and larger, what is my graph doing? Okay, is it flattening out toward a number? Remember, an asymptote is a line that a graph approaches. Okay, so I want you to take a minute and answer these true or false questions. Pause the video for just a second, think about them, and then we'll discuss them. Number one, true or false, a function cannot intersect a horizontal asymptote. This is a misconception. It's actually false. And we have in our heads sometimes that a graph never crosses an asymptote, but remember, a horizontal asymptote is called an end behavior asymptote. Okay? That means it really only tells me what's happening for extremely large or small values of x. So as I'm close to 0, sometimes the graph can intersect with a horizontal asymptote. It can cross. But as we get closer and closer to the end, it's going to approach the line instead of crossing it. So close to 0, the horizontal asymptote doesn't tell me anything about what's going on. Okay, number two, a function cannot intersect a vertical asymptote, and that one is actually true because a vertical asymptote is a non-removable discontinuity. Since it's a discontinuity, it's a place where the graph breaks, then the graph cannot cross a vertical asymptote. Okay, so those are two very different concepts. Even though they're both asymptotes, the graph can cross a horizontal. It doesn't happen often, but it is possible. But it will never cross a vertical asymptote because that is a complete break in the graph. Okay, so how do you determine where horizontal asymptotes are located? Okay, this is a little bit different than the vertical. We're going to look at the degree, or the highest exponent, in the numerator and the denominator. And there are only three things that can happen. Either the numerator degree is greater than the denominator, the numerator is less degree than the denominator, or the two degrees are equal to each other. So you're going to have to memorize these three rules for horizontal asymptotes. Okay, so if the numerator has a higher degree than the denominator, as in this example at the end, the degree, remember, is the highest exponent, so this is x squared. This is x to the first, so the top is bigger than the bottom. It is top heavy. If it's top heavy, there is no horizontal asymptote. So as we get further and further away from 0, that graph is not flattening out. Okay, if the degree of the numerator is less than the denominator, as in this example, because it's got x to the first over x to the second, so this one is bottom heavy. Anytime the degree of the bottom is larger than the top, your asymptote will be at y equals 0, which is the x-axis. So it's going to approach the x-axis as we get further and further away from 0. When the two degrees are equal, as in this last example, 5x over 2x, they're both a degree of 1, then we're going to look at the lead coefficients, the numbers in front of that variable with the highest exponent. And we're going to take the ratio of lead coefficients. So the horizontal asymptote for this example would be y equals 5/2. Okay, so ratio of lead coefficients when the degrees are equal. If it's top heavy, no horizontal asymptote. If it's bottom heavy, then it will always be y equals 0 or the x-axis. Now remember, when we're writing the down where the asymptotes are located, we always need an equation. Horizontal is y equals. If it's a vertical asymptote, it's x equal. We need this to be the equation of a line. Here are 4 examples. I'd like you to use your rules, use your chart, pause the video, and see what you get for the horizontal asymptotes. And then when you're ready, start the video again. Okay, so number 1 is bottom heavy. Degree of the top is 1, degree of the bottom is 2. When it's bottom heavy, your asymptote is at y equals 0, or the x-axis. For number 2, these both have a degree of 2 on the top and the bottom. So we're going to look at the lead coefficients, the numbers in front of those x squareds. And we've got a 2, and no number is understood to be a 1. So my asymptote is at y equals 2. Okay, for the third one, the degree of the top is 3. The degree on the bottom is 2. If it's top heavy, there is no horizontal asymptote. This graph is not flattening out on the ends. And for number 4, again, we've got equal degrees. They're both x to the first. So we're going to look at the numbers in front, which would be a 1 and a 3. So the horizontal asymptote is y equals 1/3. If you missed any of these questions and you don't understand, put a question mark beside it so that you can ask in class. Okay, the other type of asymptote, the last type, is called a slant asymptote, which is also known as an oblique asymptote. A rational function will have a slant asymptote if the degree of the numerator is greater than the degree of the denominator. Okay, so true or false? Can a function have both a horizontal and a slant asymptote? Well, I hope you answered false, because remember we just said a slant asymptote occurs when the numerator degree is larger than the denominator. And if you look back at your rules for horizontal asymptotes, if it's top heavy, there is no horizontal asymptote. So a graph can have either a slant or a horizontal asymptote. It cannot have both. So how do you determine the equation for slant asymptotes? You're going to take the numerator and divide it by the denominator, and then we're going to ignore the remainder. So you're going to have to remember your rules for long division and synthetic division to find the slant asymptotes. Here's an example. Again, it's top heavy because it's x cubed over x squared, so we know it's going to have a slant asymptote. And to get the equation for the slant asymptote, I'm going to have to do some division. So I'm going to have to say x squared minus 1 divided into the numerator, 3x cubed plus 2x squared plus 2. I'm going to leave some space in here because it skips the x. And to keep things lined up in long division, we might need a space for an x. Okay, so remember when we're doing long division, we take the first term of the divisor and the dividend, and we divide those out. So 3x cubed divided by x squared would be 3x. Okay, second step is multiply. 3x times x squared minus 1 will be 3x squared minus 3x. And again, I need to keep things lined up. Then we subtract. And I'm going to change the signs here because if I subtract a negative, it's going to change to positive. The first set should cancel out. So now I have 2x squared plus 3x. I'm going to bring down the 2. Start the process over. So 2x squared divided by the x squared would be a 2. I multiply the 2 times x squared minus 1, so 2x squared minus 2, and again, keep things lined up. I'm subtracting, so I'm changing the signs. The 2x squareds cancel out, and I'm left with 3x plus 4. I can't divide 3x by x squared, so this is my remainder. But since I am finding slant asymptotes, I'm going to ignore the remainder, and my slant asymptote is at y equals 3x plus 2. So I would have to graph that line for my asymptote. It's called a slant asymptote because it has a slope and it slants. It's not horizontal or vertical. Okay, now on this problem, I had to use long division because in the denominator I had an x squared. Remember, you can only use synthetic division if it's a 1x to the first. So since this was not an x to the first, I had to use long division. Okay, I want you to try this one, so pause the video and work this problem out, and then start it back up when you've got an answer. Again, this one has a slant asymptote because the degree of the numerator is 2, the degree of the denominator is 1. When it's top heavy, it has a slant asymptote instead of a horizontal. Okay, so this time I can actually use synthetic division, so let's practice with synthetic division because it's x to the first. Okay, so if it's x minus 4 in the denominator, I'm going to put a positive 4. And then I need the coefficients, and it doesn't skip anything, so 2x squared, the negative 3 is in front of the x, and a 1 for the constant. Skip a line, bring down the 2, and then remember we're going to multiply and add all the way across. So 2 times 4 is 8, negative 3 plus 8 is 5, 5 times 4 is 20, 20 plus 1 is 21. Okay, now again, the last number is the remainder. I don't need the remainder when I'm finding slant asymptotes. And remember, we also drop our x values or our degree by 1 for our answer. So if it was x squared to start, this is going to be 2x to the first and then my constant. So my answer is going to be y equals 2x plus 5 for the slant asymptote. Okay, so now let's put this all together. What do we need to know before we can sketch the function? We will not have a calculator to use on this portion. So far, what we've talked about are vertical asymptotes, horizontal asymptotes, slant asymptotes, x and y intercepts. So we're going to list all of those things before we try to draw the sketch. So here's an example, and let's make our list of the things we need to know. Vertical asymptote, horizontal asymptotes, slant asymptotes, x-intercepts, and y-intercepts. If you forgot how to find vertical x-intercepts or y-intercepts, go back to video 1 and it will explain how to find those things. Okay, so vertical asymptotes, we're going to set the denominator equal to 0. So if x minus 4 equals 0, that means I have a vertical asymptote at x equals 4. Okay, for horizontal asymptotes, I'm going to look at the degrees. The numerator has a degree of 1 and the denominator has a degree of 1. So we take the leading coefficients, and since there's not a number on the bottom, it's an understood 1. So y equals 3 over 1 or 3. If my function has a horizontal asymptote, it cannot have a slant asymptote. It's got either or. But when you're working these problems out, I still want you to write slant asymptote and show me that you know that there isn't one. Okay, x-intercepts. X-intercept is when your y equals 0, but on a fraction, that means the numerator has to equal 0, because if you have 0 over anything, you still get 0. So 3x plus 5 equals 0. And we solve for x, and we're going to get x equals negative 5/3. So on our graph, that will be the point -5/3 and 0. For y-intercepts, we let the x be 0. So 3 times 0 plus 5 over 0 minus 4 gives me 5 over -4 for the y-intercept. Now, let's sketch. We're going to sketch these things that we know, and then we're going to see if we need any more points to be able to fill in our graph. So the vertical asymptote is at x equals 4. So over here at +4, vertical line, and when you're drawing asymptotes, draw a dotted line that's not actually a part of the graph, it's just what we want to approach. A horizontal asymptote at y equals 3, so that's going to be a horizontal line crossing the axis at 3. And when you're finished, I want you to keep in mind that something has to happen on the left side of that vertical asymptote and the right side of the vertical asymptote. So the whole graph won't be contained just in one side. Okay, there's no slant asymptote, but I've got 2 points I can put on my graph, and that is my x-intercept at -5/3, which is -1 2/3, or close to -2, and a y-intercept at -5/4, or just a little bit past the -1. Okay, and remember what the parent function looks like. The parent function of y equals 1 over x looks like this. So our graph is usually going to look like this. Now there are a few that, if it has more than one vertical asymptote, it will look a little different. But we need a graph that looks something like this. And I've got 2 points that my graph goes through. So I'm just going to make my graph go through those 2 points, and it's going to follow the asymptotes. But that can't be the only part. Okay, so if I don't have any points on this right side of my vertical asymptote, what I can do is I can say, this is the point at 5. This is where x is 5. If I plug in 5 into my equation, 3 times 5 plus 5 over 5 minus 4, that would give me 20 over 1, or 20. So at 5, my graph goes up to 20, which is way off my grid, but probably this part of the graph is going to look something like this. It's going to follow the asymptote and look like the parent function, but notice that things have been shifted because of the other numbers in the equation. If there was anything you don't understand, put a question mark and write out what you're confused on so that we can clear those questions in class. Okay, if you will pause the video for just a minute and list all of the asymptotes and intercepts before you try to sketch, and then we will check that before going on. But if you will try this one on your own first, then you will know if you have a grasp on this concept or not. Okay, so before we sketch, we need to know where the vertical asymptotes, horizontal asymptotes, and slant asymptotes are. We need to know if we have an x-intercept, and we need to find our y-intercepts. Okay. So for vertical asymptote, we take the denominator equal to 0. The denominator this time is just x, so x equals 0. That is on the y-axis, so the y-axis is going to serve as our vertical asymptote. Horizontal asymptote, we've got the numerator larger degree than the denominator, so when it's top heavy, there is no horizontal asymptote. Instead, we have a slant asymptote. So we need to divide x into the x squared minus 2x plus 1. And since the denominator is a single term, just divide the x into everything. So y equals x squared divided by x would just be x. Negative 2x divided by x is negative 2. 1 divided by x would be your remainder, but we ignore the remainder for slant asymptotes. For x-intercepts, we take the numerator and make it equal to 0. So x squared minus 2x plus 1 equals 0. We're going to have to factor that, and this one actually factors to x minus 1 times x minus 1, which means it's a double root. Okay, so we're going to have x equals 1 for both of those factors. So it's going to hit the x-axis at 1. For our y-intercept, we're going to plug in 0 everywhere we see an x. So 0 squared minus 2 times 0 plus 1 over 0. So if I get a 0 on the bottom, that's telling me that there is no y-intercept, which makes sense because the y-axis was our vertical asymptote, and we said earlier that a graph cannot cross a vertical asymptote. So let's sketch the information we have so that we can see if we need any more to draw this graph. Okay, we're going to start with the asymptote. The vertical asymptote is on the y-axis, x equals 0. And the slant asymptote is the equation of the line. X minus 2 is going to cross the y-axis, so it has a y-intercept of -2 and a slope of 1. Okay, so we're going to have an asymptote at that line. Now we said we had an x-intercept at 1. Okay, and our graph has to follow the asymptotes. So on this right side over here, it's going to look something like this. Okay, now I don't know what's happening on the left side, so let's just pick a number. Let's say -1, and let's plug that into our function. So -1 squared minus 2 times -1 plus 1 over -1. So that would be 1 plus 2 plus 1 over -1, or -4. So -1, -4 is a point on my graph, which is showing me that the rest of the graph is down here in this little section. And usually they are in opposite sections like that on a slant asymptote, but if you're not sure, you can always test a point and find the y value. Okay, be sure that you put a question mark or write yourself some questions of anything that you need clarified in class. In our next video, we will be discussing holes in the graph.